Hello, this is Chuck Ridgway, the Automation Technology Manager here at Horner. Thank you for joining us for another Tuesday live stream. I think we've got some good material for you today. Today is all about integrating stepper motors with Horner OCS. And joining me again today is Mr. Casey Gardner. How are we doing today, Casey?
Hey, not too bad. How's it going, Chuck?
That's going pretty well. I was just double checking the audio there, making sure everything looked good. I'm a little older than you, as most people can tell just from looking at the screen, and I've spent a good part of my career working on both steppers and more recently, of course, plenty of servos as well. What kind of experience level do you have with steppers and servos?
Just a little bit more experience, mostly on the servo side, but not a lot of stepper control. I think maybe some basic cutting applications, but that's probably about it. But a lot of that's due to probably cost and selection choice for the application, right?
Yeah, absolutely. I mean, one of the things that steppers do have over servos is cost advantages, simplicity advantages. I mean, they're a lot easier to work with typically, a lot less complicated. They work open loop, all that kind of good stuff. So cost is certainly one of the biggest reasons why someone would go stepper instead of a servo in an application where both could work.
Absolutely.
All right, very good. Okay, so Casey's going to be manning the chat today, as he always does, very capably, making sure I don't do anything too stupid or screw up too badly. Meanwhile, at the end of the at the end of the presentation, we'll get back together. Casey will let me know what I've missed and what questions you may have had. Feel free to chat those at any time. We'll also have a poll question for those of you who are watching on Big Marker, and those of you on YouTube, you'll be able to answer via the YouTube chat. Okay, let's go ahead and get started. So, today's topic again, integrating stepper motors with the Horner OCS. Let's take a look at the outline of today's material. So, of course, what is a stepper motor? That's a logical place to start. We'll take a look at the advantages and the disadvantages of steppers. I know a lot of people probably are under the misconception that with the advancements in servo technology that there really isn't much of a place for steppers anymore. Certainly not the case. Servos can be used in a much wider range of applications, but steppers certainly have their place and some definite advantages as well. Of course, we'll compare with servos just so you have a general idea of what you're looking at in terms of application. We're going to talk pretty extensively about the trapezoidal move profile, which is the traditional way of interfacing and controlling steppers, using the step and direction control approach, which we will cover in great detail because that's part of the simplicity of steppers. There are plenty of other ways you can integrate steppers as well. We'll talk about that a little bit as well. And then we've got a hands-on demo scheduled for you. Okay, so what is a stepper motor? Well, it's a type of brushless DC motor that's used in simple positioning applications. Effectively, what you have is you've got a motor whose full motor rotation is divided into a number of equal steps. Steppers are known for their ability to perform accurate positioning even in open loop applications. That's probably, besides cost, that's probably the biggest advantage of steppers is the fact that they work pretty well open loop. And frankly, in the applications where they do work well open loop, that's probably when you're going to want to use them. So how do stepper motors work? Well, if you take a look at traditional stepper motor construction, you effectively have a rotor, which is a permanent magnet, and then the stator is constructed with multiple electromagnets. And then by manipulating the currents to the stator windings, the rotor will align to a specific position of rotation. So that's the basic concept behind the stepper motor. Now there's other constructions besides the permanent magnet rotor stepper motor, but that's the most common, that's the traditional. I thought I would just introduce that one to you. Now in terms of the step movements, of course it varies by the construction of the motor. Now generally what's considered a full step is when two phases are always on. And in that scenario, you're typically looking at 200 steps per revolution, at least typically. In half-stepping mode, the control or the drive that's driving the motor will effectively alternate between 1 and 2 phases being on. That will give you double the resolution with about 70% or so of the torque that you would have in full step mode. And then of course these days, by far the most common way of controlling a stepper motor from a drive is through what's called micro stepping. So in that scenario, the current really kind of approximates an AC sine wave, and the number of steps per revolution can be very large. I mean, it could be 1,600 steps, or it could be literally hundreds of thousands of steps. Now let's take a look at the advantages of stepper motors. Well, first of all, we've talked about this in the opening. They are relatively low cost. So you're going to save somewhere in the neighborhood of 20 to 30% over the cost of a servo-based system when you're talking about a stepper. We've also already mentioned the fact that they work well in an open loop configuration, a key benefit because it means there's less components that are required. You don't need an encoder with the system, and it will work reliably, again, in an open loop configuration. Steppers are quite easy to use. There's a variety of ways to control them, from very simple ways to very complex ways, but they're generally, as a rule of thumb, significantly easier to use than servos, for instance. And steppers are excellent with low-speed continuous torque applications, as well as applications where holding torque is a critical component. And because of the fact that steppers are open loop and the way they work, you do not have any hunting going on at rest. So when the rotor is stationary, generally it holds well without hunting around for position, like you sometimes find in servo applications. Now, disadvantages, and there are plenty with stepper motors. You're not going to use them everywhere for sure. They really are designed for relatively low speed. So you're typically looking at 1,000 RPM and less. And as I mentioned, they have great holding torque and low speed torque, but the torque drops considerably as the speed increases. They also don't do well with correcting for disturbances. So that's why they're best used in an open loop scenario where you don't have those scenarios and where the positioning is not subject to those sort of errors. Also, the control is typically not sophisticated. Now, that's an advantage and a disadvantage. So if you have a fairly sophisticated motion profile you need to follow, generally steppers are probably not the approach you're going to take. And also, they can be a bit of a power hog from time to time, because at rest they have that great holding torque, but often it is at the expense of utilizing full power at rest. Now, there is a scenario where with some stepper motors, if the detent torque is adequate to hold your load, then you do have the ability to reduce that power at rest. So definitely advantages and definitely disadvantages. Now, as we compare steppers and servos, and this is not an exhaustive comparison, but it's always good to take a quick look at what the options are here. So again, with steppers, those are typically run open loop. They enjoy, usually in a typical system, a 20 to 30% cost savings. They offer good low speed torque. All right, servos are operated on a closed loop. They can operate at much higher speeds. They are more accurate, can handle more sophisticated motion profiles for sure. Now, one of the charts I'm going to show you there on the right, we're not going to go crazy with charts, but that's a pretty good indicator of some of the characteristics of servos and steppers. So the green line there indicates the torque of steppers, and you can see that as the speed goes up from zero, the torque quite quickly goes down. All right, and then if you look at the red line, that is the instantaneous torque for the servo, and the blue line is the constant torque line for the servo. So as you can kind of tell from that line, if you've got an application where the torque requirements are not continuous, then servos have a significant advantage over steppers in that they can supply a pretty high level of peak torque. However, if you need continuous torque, then there is certainly a low speed range where steppers have a significant advantage. So just a good opportunity to take a look at the comparing and contrasting steppers and servos. So after reviewing all these characteristics, when is the right time to use a stepper? Well, certainly in low cost applications, low speed applications, applications where you're doing point-to-point movement, applications where the continuous torque at low speeds without the benefit of a gearbox or other mechanical advantage. In those sorts of applications, indexing for instance, it can be a significant advantage to go with stepper. But again, in most other applications, you're going to be looking at servos. Now let's talk about the different components in the control system when you're talking about controlling stepper motors. And we've really got four main components here. And it starts with the controller. And when I'm talking about controller, I'm talking about a PLC, I'm talking about a Horner OCS All-in-one Controller. If it's PC control, it could be a personal computer. So whatever is driving the logic of the system, that controller is logically determining the required position of the motor based on the conditions. The next component in line is called an indexer, and that effectively commands the move by generating a number of steps or a pulse train. We talked about the fact that with steppers, you're going to have a certain number of steps per revolution, or pulses per revolution that is sometimes referred. And the indexer is typically the component traditionally that provides those pulses to the next component, which is the stepper drive, sometimes called a driver, sometimes called a translate driver, you name it. But basically what the drive does is it takes those pulses, those low voltage pulses, and it converts those, translate those effectively into the required motor currents to cause the motor to actually turn to that particular position. So it presents the appropriate motor currents to get the shaft from where it is now to where it needs to be. And the motor, of course, is the mechanical component that's actually doing the work, performing the mechanical motion. So those are the four different components: controller, indexer, drive, and motor. Now, just like the OCS is an integrated piece of equipment, one thing that has happened over the past several years is an increase in the integration of the components in a stepper motor system. So very often today, you'll see that the controller and the indexer are one component, and that the drive and motor are often one component as well when it comes to steppers. Integrated steppers with drives is extremely popular. So on the next slide, you can kind of take a look at where we're heading to. On the left, you've got the Horner OCS All-in-one Controller, which acts as the controller for the system as well as the stepper indexer. And on the right, I'm showing a very common these days component, which is effectively an integrated drive plus motor. So these integrations have really made the whole stepper motor control system a lot more streamlined and a lot easier to deal with, certainly from a wiring standpoint and from other aspects as well. Now, a pulse train style interface like I've been talking about recently, at least in the last couple slides, is certainly the traditional way of interfacing a controller like an OCS with a stepper motor. And we've been supporting stepper indexer functionality for many, many years, certainly almost all of my career here at Horner. Now, there are other options as well, more modern options, I guess you could say, that offer more capability, but also with increased complexity. And part of the beauty of steppers is they're pretty simple to operate. That being said, if you've got a stepper application with any complexity at all, you should definitely evaluate other options beyond just step and direction. And that would include Modbus TCP, which is not known as a high-performance communications network, but in a lot of stepper applications, that's okay. It's easy to use, it's easy to implement, and the lack of performance is not an issue in a lot of cases. Or another option that is a field bus type option is CAN Open. And last month we spent a fair amount of time on CAN Open talking about its virtues when it comes to motion control applications. That's true with servos, it's also true with steppers as well. I've spent a fair amount of my time working on steppers, as well as servos for that matter, with CAN Open as the interface. Certainly not the only way I've worked on the systems, but that's certainly a good option these days. So pulse train is certainly what we're going to focus on today. So the bulk of the remaining program will be covering that because that's something that people are interested in. But just be aware that Modbus TCP and CAN Open are also options for the Horner OCS. Okay, so as we start to talk about the traditional means of controlling a stepper motor, which is the step and direction pulse train style interface, we certainly need to talk about the trapezoidal move profile. So what you see on the chart there to the right, and we'll be looking at this chart quite extensively for the next few minutes or so, is we have a velocity versus time chart, okay, and there are certain parameters which we need to define for the trapezoidal move profile. And that starts with starting velocity. So that is the speed, could be in pulses per second, could be in inches per second, etc. But that's the speed at which the stepper motor will begin operating, okay? And then it will accelerate up to running velocity, which also, of course, is in pulses per second or inches per second, whatever the case may be. So we start out at starting velocity, we accelerate up to running velocity, we run along at a continuous speed for a while, then we decelerate. So in addition to starting velocity and running velocity, we also have acceleration time that we need to define, we have deceleration time we need to define, and then we have running time that we need to define. So all those are different parameters in a trapezoidal type move profile. And you'll hear it expressed with slightly different units and slightly different parameters from time to time. Now in the Horner OCS, certainly in the XL series products, from the XL4 on up, and also including the X5, we have the ability to present a trapezoidal move profile in the form of a pulse train, and these are the parameters that you need to configure on the OCS side. So if you look at the user's manual for an XL4 and XL7, for instance, you'll see it expressed like this. You'll see start frequency, which effectively is the same as starting velocity. You'll have run frequency. You'll have acceleration count. So it's not in terms of pulses per second squared. It's not in terms of so many milliseconds of acceleration. It's in terms of the number of steps that you're going to send out during the acceleration phase of the trapezoid. Similarly, you have the same thing on the deceleration side, and that is a decel count as well. And then in between, you have your running count, the amount of time that you're going to be running at full speed. So if you take those three things together, the acceleration count, the running count, and the decel count, all in pulses or steps, then that is the total distance for the move. So those are the parameters that you need to define on the OCS side to define that trapezoidal move profile. Okay, so when we go from the profile on paper to actually making a motor move on a real system, what are the sorts of things that we need to think about? What are the sort of things we need to calculate? Well, first of all, there's a couple things we need to understand on the system as a whole. First of all, from a mechanical standpoint, what is the linear distance per revolution of the motor shaft? Okay, so we need to take a look at the mechanical design. Are there gearboxes involved? What is the system mechanically, etc., so that we can have a relationship between a revolution of travel of the motor shaft versus a linear travel of whatever it is that we're moving with our control system. So that's a key piece of information there, and we'll get that basically from the mechanical design. The other thing that's important to know is, how many steps per revolution, how many pulses per revolution are required for the stepper motor. So, and that's going to vary greatly by the stepper motor that you produce. And as I mentioned, these days, micro-stepping stepper motors with maybe 10,000 or 100,000 steps per revolution aren't unheard of, but then you can still get very, very inexpensive stepper motors with 200 or 400 or 1,600 steps per revolution as well. So that's another key piece of information. Now, in a lot of stepper applications, we're executing the same moves over and over again. I mean, it's very often go from point A to point B and from point B back to point A again, or move from point A to point B and then equal distance, just keep incrementing on down the line. So that's very typical with stepper type applications. But for each move that we're going to execute, we need to know, or we need to determine, how far are we going to be moving? We'll start with linear distance and then we'll convert that over to steps. What kind of acceleration and deceleration times do we need? Let's face it, I'm an electrical guy, so I don't necessarily think in terms of when I think of acceleration, I understand that it's pulses per second squared or inches per second squared or whatever the case may be. But I tend to think of in time. How long is it that we're going to be accelerating? How long is it we're going to be decelerating? What kind of starting velocities are we going to be at? What kind of full speed running velocities are going to be at? So those are all the things that you need to kind of think about ahead of time so that you're prepared to execute the control system. Okay, so let's take an example here. So let's say we've got a case where we'll keep it simple. 1 motor revolution equals 1 inch. We'll start with an example system like that. And we'll go with a fairly typical number of steps per revolution for a low-cost stepper these days. And that would be, let's say, 1,600 steps per revolution. So you can get, certainly for less than $200 for a small stepper, you can easily get a motor that'll support, an integrated motor that'll support 1,600 steps per revolution. Okay, so that'll be our example. And then we'll add to that, for our sample move, that we're going to move a distance of 5 inches. So we're going to calculate the parameters that we need to move a distance of 5 inches. We're going to go with, and again, I'm thinking in terms of time, we're going to go with an acceleration and deceleration time of about half a second. We're going to start with a starting velocity of 1/2 inch per second and bump it up to 1.5 inches per second. Okay, so that's the parameters we're going to use for our example here. Okay, so let's take a look at the trapezoid now with all this detail filled in. All right, so you can see starting velocity, running velocity, acceleration times, deceleration times, move distances, all that is filled in now. All right, now let's start calculating our parameters based on this example data. The first thing I like to do is I'm going to calculate my total distance, okay, in steps. All right, even though if you remember from the chart that I showed that showed what parameters you need to specify, the total number of steps wasn't one of those. I still like to do that first. So we're going to make a 5-inch move, and we've said that our mechanical system is 1 inch per revolution, and we've got 1,600 pulses per revolution. So that means this particular move is going to be a total of 8,000 pulses. Okay, so that's what we've created. Now that's not going to be a direct parameter for anything we do, but it's a useful thing to know for calculations later. All right, next we're going to calculate our starting and our running velocity. So how do we do that? Well, we've said that we're going to start with a 1/2 inch per second as our starting velocity, and then we're going to accelerate up to 1.5 inches per second. So if we take those values, multiply by the number of pulses per inch, and remember, as it's nice and easy math here, we've got 1,600 pulses per rev and 1 inch per rev. So when we do that quick math, we can get 800 pulses per second for starting velocity and 2,400 pulses per second for our running velocity. Okay, the next thing we have to calculate are the number of acceleration pulses and the number of deceleration pulses. Now, how do we calculate that? Because keep in mind that during the acceleration phase, and the deceleration phase for that matter, we're starting at one speed and ending at another. So generally, that means what you're going to want to do to calculate how many pulses you have during the acceleration phase or the deceleration phase is you're going to actually take the average number of pulses during accel and the average number of pulses during decel to calculate what that number turns out to be. And since we're accelerating from 800 to 2,400, for instance, the average of that is 1,600 pulses per second. And then when we convert from 1/2 a second over to pulses, we do the additional multiplication and we see that there are 800 pulses during the acceleration phase, and because we're going with an equal number of, or an equal acceleration and deceleration, we've got the same thing on the deceleration phase. Okay, now keep in mind, my example shows accel and decel being identical. It certainly doesn't have to be that way, and there's a lot of applications where it would not. But for the ease of this example, I'm keeping them the same. Okay, so we've got almost everything we need now to execute our move. The only thing we don't really have is the number of running pulses that we need. Now, and the reason I calculated the total pulses at the beginning was the way that we come up with our running pulses is we take our total minus our accel minus our decel, and what's left is going to be the number of pulses we execute during the running phase or the full velocity phase. And after we do the math, it's 6,400 pulses. Okay, so here's a summary of our parameters, and these are the parameters that we need to plug into the OCS. We did a calculation on total move distance, even though that's not a parameter we plug in directly. Starting velocity of 800 pulses per second, running velocity of 2,400 pulses per second, XL and decel 800 pulses each, and running steps of 6,400 pulses. Now, how do we actually plug this data into an OCS and make all this happen? That's a question that you would have, most logically. Well, we've actually got a series of parameters that are allocated to the OCS when it is configured for stepper motor control. Okay, and we'll show the configuration in a demo here very soon. So what you have with your typical XL series OCS from the XL4 on up is you typically have the ability to drive as many as 2 stepper motors. So you've got kind of the first stepper output and the second stepper output, all right? And those have different register numbers allocated to each of them for start frequency, run frequency, acceleration, run, and deceleration counts, okay? Now, one thing to keep in mind is this map varies a little bit if you're running your XL series controller in 4 counter mode, and if you're using an XLE or an XLT, it's a little different even than that. So just wanted to throw that in there as a little bit of a disclaimer. Okay, now we've gotten the parameters that we want to execute our move. We've got those established, but how do we actually make the thing go? Well, we have a few digital bits that have been assigned to the stepper control for each of the 2 stepper systems that's available inside of an OCS. If you have configured an XL4 or an XL7, for instance, to take advantage of its stepper outputs, then effectively Q1 is the output for the first stepper, and you use that coil to trigger the start of a move, and Q2 is what you would use to trigger the second stepper that's built into the OCS. And then you've got a couple feedback bits. You've got a bit that is used to tell if the system is ready and when it's done, and you've got another bit that'll turn on if there's an error. In other words, if you've configured some parameters incorrectly, something that can't actually be executed, it'll let you know, for instance. Okay, so to kind of make this all kind of a little clearer from a sequence standpoint, I will be showing you some ladder code here shortly that executes this, but I decided it would make a lot of sense to show kind of a pseudo flowchart here on how to actually initiate a move from an OCS. So what's the process like? Well, we're going to start out by setting our move parameters. Okay, those are the AQs, etc. We are going to also set an output to control direction, because I think I briefly mentioned the fact that we consider this like a step and direction type interface with the OCS. We've talked a lot about stepper, but we haven't talked much about the direction. The step signal, or the pulse output signal, is a higher speed pulse train. The direction signal is just going to be a very low speed signal that is determining whether the motor is going clockwise or counterclockwise. That's all. All right, so we set our move parameters, we set our direction output to go the direction we want to turn. We check one of those status bits in the OCS that's built in to see if we're ready to move. If we are ready to move, we'll also trigger the move at that point. Okay, so we'll set the Q bit that triggers the move. As soon as we trigger the move, we're going to monitor for errors. Do we have any errors? If not, we continue on, verify the fact that we are indeed moving, right? Because we need to make sure we're moving. Once we've verified we're moving, then we can pay attention to the flag that tells us when we're done. When that turns on, we know we're complete. We can kind of reset and continue on and make the next move at the appropriate time. So that's the sequence that's required for commanding movement. I think what I'm going to do next, because I think my next slide is, next slide talks about an add-on accessory. I'll come back to that later. Let's go ahead and switch to Seascape. And I want to show you some of the logic and the configuration, as well as a sample screen that I've developed for testing. And then, of course, we'll turn our overhead camera on and actually try and make a stepper motor move. How about that? let's go ahead and start with hardware configuration. All right, what I have here is I have an XL7. All right, that's my controller I'm working with here. And this traditional step and direction interface is handled under local I/O. Okay, and I happen to have a Model 3 here. All right, as most of you know, or some of you know, the last digit in the part number determines what I/O has been installed at the factory. And as it turns out, Model 3, 4, 5, and 6 have solid state outputs, so they have the ability to drive stepper motors through the indexing feature. Okay, the Model 2 can also do it, but requires a special accessory that I'll cover in a little bit. But in my example here, I have a Model 3, which has 2 outputs that can be used for stepper indexing. Okay, so I'm going to go to the local I/O tab. All right, go to configuration, module setup, and I'm going to go to the digital output option here. And this is where you configure the high-speed output for stepper operation if that's what you want. Now in my case, I just have one stepper connected to the system, so I am using Q1 as a stepper output. And simply by configuring or clicking that radio button, I've enabled the stepper capability in the controller. Now, for the high-speed output functionality, you do have the ability to move around where your move parameters and your status parameters are located. You can't move your control output. You can't move your Q1 or your Q2, but you do have the ability to move your AQs and your Is if you want to. I just leave them at the defaults. They typically work well in that configuration. Okay, so that's really all the configuration that's required, and that is clicking this one radio box here, rearranging this if you choose, but I would suggest not unless you have a really good reason. Okay, so that's it for configuration. Now let's take a look at the logic. Okay, and this is a sample program that we provide to just about any customer who asks, and this program is just designed to execute sample stepper moves. Okay, that's pretty much all that it's doing. And so what we have here is that sequence. For all intents and purposes, it's the spreadsheet that I showed you, not the spreadsheet, sorry, the flow chart that I showed you. It executes that particular sequence. And it really only takes a few rungs to basically execute this. So I've got, what, 1, 2, 3, 4 rungs total for executing these moves. Very, very simple stuff. I've got some extra rungs at the bottom, but those aren't related to creating the pulse trains. Okay? All right, let's go to the screen and take a look at the screen that I built. That'll make it a little bit more obvious, you know, where you fill in the data and what you do to actually cause motion for the sample program. Okay, so this is just obviously a great big screen that allows you to select between the traditional step and direction stepper example or a more, I guess, a newer, more modern, but more complicated for sure, can open stepper example. So let's go ahead and head to the step and direction screen. Okay, so what we have here, here's where we can fill in the initial and running velocities, okay, and those are in pulses per second. On that same screen on the right side here is where we fill in how many pulses for acceleration, running, and deceleration. All right, we've got our start button here, which in the logic program, this start button is ultimately going to turn on Q1 to initiate the move. And then we have our statuses. We have our status for ready, our status that says, yep, we're moving, our status that says, yep, we're done. And all of these 3 status lights, if you will, were all derived from that same status bit that's available with the stepper interface. Okay, so just by knowing what state you're in, have you started a move, are you getting ready to start a move, are you moving but you're waiting to complete, just based on what state you're in terms of executing the move, that one feedback bit can be turned into literally 3 different status bits. And then we've got our dedicated error bit that tells us if there's a problem with our parameters. And then I've added this reset bit, which is just an extra piece of, it's just an extra feature of the example program here. And then one other last little example, or one last little feature, if you will. I've got a timer so that I can time how long the moves are taking based on the parameters that I plug in. And then I also have this save parameter button here. What that does is it triggers a rung of logic. In this example, we're just manually copying into AQ registers. And every time we power up, remember, AQ registers start out at 0. So to maintain those default values for my example, I have a save button here so that it on the first scan it'll go ahead and load in the last values that I used if I have actually saved them. Okay, so that's the example. There's not a whole lot to it. Again, there's 3 or 4 rungs of logic to keep track of the status coming back from the system. There's 1 bit that you need to turn on to initiate a move. You've got 5 parameters you have to fill in. Let's take a look at how this works. All right, I'm going to go ahead and switch over to my overhead camera. Okay, there we go. And you can see the XL7 that's executing the example program here. Okay, so what I've got here is a very, very, very inexpensive stepper motor with a traditional step and direction type interface. It is just like my example that I went through on the slide presentation. It's got 1600 pulses per revolution. Okay, I've just put a piece of tape on here so that we can keep track at least a little bit as to where the shaft is and watch it move. All right, let's go ahead and see what happens here. So I'm going to go ahead and go to the step and direction screen that I showed you earlier. All right, I've actually plugged in the parameters for initial velocity, running velocity, acceleration, deceleration pulses, and running pulses, the same ones we calculated. So you can see how ugly of a move I have actually configured here as an example. So when I press start, since we are ready, when I press start, things should start moving. Let's see what happens. All right, there we go. Okay, so my piece of tape isn't super exact, but what you have there is 5 revolutions exactly, which in our example, if there was really 1 inch of mechanical movement based on 1 revolution, the 5 revolutions would be exactly what we want. I'll go ahead and run that again. Okay, not super exciting, and again, running pretty slow depending on the system. Obviously we can play around with the parameters. Let me go ahead and let's run it one more time and time up the move. As you can see, it's taking right about 4 seconds exactly. Let's crank up the velocity a little bit. Okay, all right, and let's go ahead and make that there. All right, now I should be playing around. I should be changing these parameters over here to move the exact same amount. I'm not going to do that. I'm just going to see what happens when we increase our velocities. Let's see how it goes. Okay. All right, let's go again. Okay, so there's really not a whole lot to it, really. 3 or 4 rungs of logic, a bit to configure, not much difficult at all here. Okay, since we have a couple minutes, I just thought I would show you an alternative to the step and direction approach, and I'm not going to cover this in any detail. I'm just going to show it to you as just a little bit of a contrast here. And that is, what I have here on the right is actually an integrated servo of a similar size to what you saw with the stepper motor that I had there, that has a can open interface on it instead. Okay, so it's connected to the XL7 through CAN 2, and CAN 2 is configured for CAN open. This is actually a servo, not a stepper. Okay, although you can get steppers that have a CAN open interface, as I mentioned before. And I'm going to go back to my home page, go to the CAN open stepper example. All right, And now I'm just going to go ahead, you can see there's a lot more complexity here, right? There's a whole bunch of parameters for keeping track of the network communications. We've got a variety of different parameters in terms of acceleration, deceleration. We could be operating this in velocity mode instead of just position mode. We could be in torque mode. There's a lot more options when you're talking about a stepper system typically. And one thing you could be noticing is that the position is hunting around a little bit. Every once in a while you'll see that 4,000 move. Also, I can very easily, or at least I have the ability to, not necessarily easily, I can move the shaft a little bit there as well. But I'm going to go ahead and go to 100,000 counts and let's see what happens. So I think you probably saw there, that's a significantly, at least based on what I have it configured for here, a significantly faster bit of motion there. Okay? Alright, so I just thought it would be fun to show you just something a little bit different. Same sort of scenario, but a servo instead of a stepper, can open instead of step and direction. Just thought it would be an interesting point of comparison, if you will. Let's head back and talk about one more thing, and then we'll bring Casey in. Okay. The one additional thing that I wanted to mention was the fact that we offer an add-on accessory for the XL series that can help increase the frequency at which you can output pulses. Okay? Now, this option card is called a HE-HSQ. There's also an extra X in there as well, but I always just call it the HSQ. And this is an option card you can install in the field. So you basically pull the back cover on the back of the controller where the I/O is mounted, install this extra circuit board, and a slightly deeper back cover is included in the field installation kit. You install that back cover, and now what you have are an extra 4 terminals that, with the standard model, provides 2 high-speed outputs up to 200 kilohertz. And with the 5-volt option, you can get frequencies up into the megahertz range. Now, why is this possibly needed? Well, there's 3 functions for this accessory. Okay, the first function is just to add the frequency. If you're working with a micro-stepping motor that needs lots of pulses per second to execute its moves, then this HSQ will allow you to send out frequencies in the 200K range, even for a 24-volt pulse train. It also gives you the ability to support 5-volt rated steppers, which, because of the lower voltage, allows you now to send pulse trains that could be, again, in the megahertz range even. And then the last thing it does is this accessory gives the ability for the Model 2, which is a relay-only output version, to support stepper, okay, and PWM and frequency, which it doesn't do on its own because it only has relays. So that's the HE-X HSQ. It's an inexpensive accessory. For the right application, it's worth its weight in gold, though. All right, I'm going to bring Casey back in. All right, Casey. So, what do you think? Did I miss anything there?
Not in particular. I thought it looked pretty good. We did get one question towards the end, and I believe this is regarding the stepper moves. From Colin, he's asking, can more complex movement profiles be configured?
That's a great question, and basically the answer is no. It's pretty basic stuff here. It's just trapezoidal only. You know, there's no fancy S-curve acceleration. You know, you can't do, you know, type of index type moves or interrupted moves or any of those sorts of things. So it's pretty basic. So I guess another reason why for an OCS-based control system you would go maybe with Modbus TCP or CAN Open as another option for interfacing with a stepper motor is basically because you would have additional options for different profiles or different applications, which you couldn't do with just a simple trapezoidal, for instance. Okay.
Good question, Colin. I think that about covers
Okay, now before we move on, I did want to have Marcy go ahead and put that poll out there. And I know you can't see it on the YouTube side of things, but we've got a quick poll, and if you can answer on YouTube, that'd be great. The question basically is this. Have you used stepper systems in the past, servo systems in the past, both or neither? just a little point of information we were gathering, and we appreciate if you would answer that for us. Okay, while you do that, I want to also mention the fact that we have coming up next week, we have another Tuesday 2 o'clock live stream, and the topic for the week is wiring Horner Micro OCS. So that is going to be all about wiring the I/O, the network, all those sorts of things using the types of connectors that are available on the Micro OCS. Now, one of the things that's great about the Micro OCS, and I'm going to bring Casey back in here. One of the things that's great about the Micro OCS, it is crazy inexpensive. I mean, if you think about 30 I/O and networking and Ethernet on all the models except for the basic one, all the things you can do with the Micro, it's amazing. But one of the reasons why it's really cost effective is because it uses smaller terminal blocks. It uses RJ45s for things like CAN even. So there's some compromises that we made. But if you know what you're doing and you just use a little bit of care during the installation, it can go just perfectly smooth. But we're going to give you some information next week that'll help you with the installation go smoothly. So what's your experience been on the Micro with working with some of those connectors? Have you had to kind of adjust to that a little bit, Casey?
Maybe a little bit. It's definitely easier to take the connectors out and kind of wire them up individually than it is to try to keep them in there. But no, I mean the Micro OCS is easily, like you said, one of our best values. So you're going to have some little drawbacks like that, but you just getting over those little bumps or something like that. I
Sure.
mean, it's, for the money, it's pretty hard to beat.
And one of the things that we'll talk about is, when you can, if you reduce your wire size a little bit. A lot of us are used to, especially old timers like me, we're used to using that 14 gauge on everything, right? Even in scenarios where it's really not needed. So we're going to talk about appropriate wire gauges and all those sorts of things next week. Should be a good session for sure. Okay, very good.
Perfect.
Excellent. Okay, so again, as a reminder, join us next week for wiring Horner OCS microcontrollers. Okay, so that's going to be it for today's program on integrating stepper motors with the Horner OCS. We thank you for joining us, whether you're watching live or on replay, and we look forward to seeing you again next week for our next topic.